This is Mr. Cardoso, and in this video we are going to look at section 2.4 in advanced functions, and in particular we're looking at Manny's walk to school. So over here on the y-axis we have the displacement or the distance, so this could be height, or in this case it is distance from the starting point, so this is the starting point. Since Manny's walking to school, the starting point will probably be Manny's home, and the end point would then be school. So this is the distance that Manny has walked from school. And over here we have the time, so how long it's been. So Manny's walked to school. So we can see that Manny starts, walking to school. Something happens here, so we can sort of tell a story of what's going on from the graph. So Manny walks to school. He's walking towards school. Then he stops. And you can see this is in seconds, so maybe for 2 seconds Manny is stopped. And you can tell that he stopped because the graph or the distance from school is not changing, it's not going forward, it's not increasing or it's not decreasing. His distance is remaining at 4 meters from school, or sorry, from home. His distance from home is staying at a constant 4 meters, as you can see here on the y-axis. So that's how we know he stopped. Then he starts walking towards school again. Now, what can you tell me about this walk towards school as opposed to this walk? Well, we'll look into that a little bit further, but here you can see he's walking a bit slower to school than here. And you can tell that from the slope of the graph. Okay, it's the slope or the rate of change is not as high as it is here, because this line is steeper than this one. Okay. And then at this point, after about 6 meters that he's walked from home, 6 meters, something happens here and he changes direction, and then you can see that as the distance from home starts decreasing. So that means he starts walking back towards home. So maybe Manny forgot something. Maybe he forgot his ID tag, and so he's going home like a responsible student to get it. Okay, so this is Manny's walk. You can see the distance in meters here and the seconds that's taking place. So let's take a deeper look at this and see how this relates to rates of change. We've talked in this chapter a lot about average rates of change and instantaneous rates of change. We know that the average rate of change is the slope of the secant line, or the slope of the chord, and instantaneous rate of change is the slope of the tangent. Well, here at any point along this segment BC, if I find the slope of the tangent, it's going to be equal to the slope of the line segment itself. That's because it's a line, or it's a linear segment, so the slope will remain constant throughout that line segment. So let me go ahead and find the slope of that line. You can just do rise over run. You can calculate it very easily. Okay, so if I display it there, you can see the rise here is 2, the run is 1, so the slope then will be 2. So I can display the slope of BC. So if we take the units into account, that becomes meters, which is the rise, and seconds, which is the run. So the slope of BC is 2 meters per second. And that's basically how fast Manny is walking in this section. Okay, so what's the slope of this line? The slope of this line is going to be 0. Okay, that's because the rise is 0. Even though the run here happens to be 4 from 2 to 6, the rise is 0. So it's 0 over 1, and the slope then is 0. And of course, then that's 0 meters per second. Then for the next part, if we find the slope of that part here, okay, and I display that on the graph, you can see here it's 0.33 meters per second. So again, just finding y2 minus y1 over x2 minus x1. And then finally, for the last segment, EF, okay, display it there, and we can see that the slope of line segment EF is -1 meters per second. So what does this all mean? This slope of this line segment here, 2 meters per second, as we have said, is actually Manny's speed. So when we look at a displacement time graph and we figure out the slopes of that graph, the slopes tell us something about the speed at which Manny is walking to school. So here, since Manny is stopped, his speed or velocity is 0. Here, Manny's walking at a speed of 2 meters per second. Here, Manny is walking at a speed of 0.33 meters per second. And here, Manny's walking at a speed of -1 meters per second. Well, that sounds kind of odd that he's walking at a speed of -1 meters per second. And it is odd. Really, his speed is 1 meter per second. What does the negative mean? The negative means that he's actually going back towards home. The direction has changed. So the negative indicates that he's decreasing, or his distance from home is now decreasing. Whereas here, his distance from home is increasing, hence the positive slopes. Here, the distance from home is decreasing, hence the negative slopes. Okay, so this was an example, a simple example, where we have a bunch of line segments. So the slope of or the average rate of change, or the slope of the secant, is the same as the instantaneous rate of change at any point on that segment, since it is linear. Okay, let's look at a more complex example. So I'm going to hide all of this now, and we'll look at some curves. So I'm just going to get rid of all this stuff. Bear with me for a second. Okay, hide this, and I need to hide a few more things. Hide these points here. Okay, so now let's take a look at a function. Okay, so let's pretend now Manny is following this path towards school. So what could you tell me about Manny's walk to school now? Well, you can see that at the beginning, he starts walking fast and then he's slowing down. Well, how can we tell? Now, the average rate of change is not the same as the instantaneous rate of change at any one point. Okay, if you find the average rate of change, you can between any 2 points, it would be an obvious secant line. But here, if we want to find the instantaneous rate of change at any one point, we need to find the slope of the tangent at that point. So I'm going to draw a point here. Sorry. And that's the tangent line, sorry, and here's the point. And so this is the point. I should actually start by drawing the point first, then draw the tangent line to that point, and here I have the slope, and I'm going to display the slope here. There we have it. Okay, so you can see it a little bit bigger. Now, if I take this point and go through Manny's walk. So when I go through Manny's walk, I'm going to start at the beginning. So at the beginning, the tangent, you can see the tangent line here, is actually at the very beginning going to become vertical. Now that's not really possible, because really that means that Manny is walking at an infinite speed. So that's not really possible. But let's just look beyond that point right now. So here, Manny starts walking pretty fast. You can see the slope of the tangent is 4.35 meters per second. So he's walking at a speed of 4.35 meters per second. But as Manny keeps on walking to school, while his displacement from school, or his distance from home is increasing, so he's getting further and further away from home. As you can see, the graph is going up. His speed, which is given by the instantaneous rate of change, is actually decreasing. Okay, so let's repeat that one more time. So you can see the graph is actually going up, and his displacement, or distance from home, is increasing. He is getting farther and farther away from home. But even though he is getting farther and farther away from home, his rate of change, or his speed, starts high, which means he starts walking fast, and then he starts slowing down. Okay, and he continues to slow down, and his instantaneous rate of change is decreasing. So he's still walking towards school, as you can tell by the increasing graph, but the speed at which he's walking, he's constantly slowing down. He's getting slower and slower as he continues to walk to school. And you can see that from the slope of the tangent, or his instantaneous rate of change. So now at this point, for example, he's going at 0.24 meters per second, whereas at the beginning, he was going close to, 5 meters per second, 6 meters per second. Well, really, that point here is infinite, but we'll ignore that point for now. Let's look at one more example. So I'm going to hide this, and we'll look at an example where Manny's walk to school is actually decreasing and then increasing on a curve. So let's get rid of this. I'm just going to hide some of these things here. Bear with me a moment. And I've got to remove the function itself. Okay, and there we have it. Okay, so now let's look at another function here. Let's ignore the left side of this, so we're just going to look at the right side, as this graph only makes sense for positive time. Okay, so we're going to look at this graph now, and I should draw a point, a tangent point that where I want to find the instantaneous rate of change, and then I can draw a tangent line at that point, and then I can figure out the slope of that tangent line. Okay, and then I want to display that slope. Where is it? I think it's this one. No. No, it's not that one. I lost my slope here. Well, no worries. I can add it again. And I want to say I want the slope of F3. There it is, 2.81. I'm just going to make it a little bit bigger so you can see. So there's my slope, okay, of that point. Now, let's take a look at Manny's walk to school this time. So this time, if we go back to 0 at the origin, Manny starts walking to school at a speed of 0 meters per second. So he starts really slow. And you can see his distance from home is increasing. So he's getting further and further away from home. Now, if I take this point, oh, I lost my point here. I'm trying to get that back. Okay, if I take that point, I won't go right to the origin this time. If I take that point and start moving it to the right, you can see the slope of the tangent is 0.54 meters per second there. And then here it's 1.1. And then you can see here it's 2, and then 3. So you can see in this kind of graph, while he's getting further and further away from home, he's doing so at a faster and faster pace all the time. So he starts increasing. He starts walking slow. He's walking slowly to school, and then he's walking faster, and then he starts running, and then he starts running really, really fast, and then he gets faster and faster, because this is his speed in meters per second. So he's getting faster and faster as time goes on. So this is just a way of understanding that the slopes of the tangents, or the instantaneous rates of change at any point on a curve, will tell you how fast the rate of change is at that point, and how things are changing. So this is very different from the last graph. Sorry, the last graph that we saw, if we compare the two, while his distance from home is increasing in both cases, this one he starts walking fast and slows down. And in this one, he starts walking slow and speeds up. Okay, so those are some examples of how we can use graphs, tangents, and instantaneous rates of change to get a lot of information about what's going on in a graph and what's going on in real life. Okay, hope you understood that, and we'll see you next time.